Good afternoon, everyone. My name is Nathan Wei. I'm a PhD student in Professor John DeBerry's group at Caltech, and today I will be sharing some work that we've done over the past year or so on surging wind turbines. And by surge, we mean streamwise motions of a wind turbine relative to a stationary frame. Now, you might be thinking, why in the world would we study moving wind turbines? Isn't turbine motion like a sign that something has gone horribly wrong? Well, on land perhaps, but floating offshore wind turbines and turbines mounted to crosswind kites will move around by design. These turbines can capitalize on stronger winds that are found in previously inaccessible areas and thus make promising contributors to global energy demands. Now, the power production and fatigue loads of these types of turbines will depend on their response to surge motions. Therefore, if we can model these dynamics, that will inform the design and control of these systems for improved efficiency and longer lifespans. And so in this study, we seek to explore the dynamics of a periodically surging turbine through experiments and modeling. So first, this is our experiment shown on the left schematically and in a video on the right in which the turbine is moving through the largest surge motion that we tested. Our apparatus consists of a 3-bladed horizontal axis wind turbine, which is electrically loaded using a generator and then fixed and variable resistors. We measure rotation rate and torque directly from the turbine shaft, and the turbine sits on a traverse that slides along 2 rails for a total stroke length of 1.5 meters, and this is actuated by a magnetic piston-type linear actuator. The apparatus is mounted in a 10-foot square fan array wind tunnel, which we run at a wind speed of 8.1 meters per second, and that corresponds to a diameter-based Reynolds number of around 610,000. We actuated the turbine through different types of surge velocity waveforms, including sinusoidal profiles and what we call trapezoidal profiles, which range from square waves to triangle waves in velocity. And these were conducted over a range of surge frequencies and amplitudes, with velocities up to 23% of the wind speed, as well as over 6 different tip speed ratios, which simply means how fast the blade tip is moving relative to the wind speed. So for each experimental case, we ran the system for 100 motion periods and took a phase average, and then compared those results with a steady reference case taken at the same wind speed and load, but with no surge motions. And so now, what do we expect to see? Well, if we make a quasi-steady assumption and we say that power scales as the wind speed cubed, then we can take our surge waveform and get an ideal prediction for power. But if we plot the measured data for this case, the phase and amplitude do not match the model. It looks like the missing dynamics are acting like a low-pass filter on the quasi-steady prediction. And so given that ansatz, we can drop the cubic nonlinearity and simply take a linear systems approach. And so we derive this model for the system dynamics. The model is an ordinary differential equation that is first order in time and linear in the surge velocity and the rotation rate. And this allows us to derive analytical transfer functions and thereby obtain amplitude and phase predictions for a given periodic surge forcing. Derivation details can be found in our manuscript at this link here. And where does this model come from? Well, it's just Newton's second law, where the right-hand side represents the net torque on the turbine. The first 2 terms represent a local linearization of the aerodynamic torque in steady flow as a function of wind speed and rotation rate. And the second 2 terms come from a first-order model of the generator torque, which is what we measure on the turbine shaft. And it's worth noting here that all of the model coefficients can be computed from torque measurements taken in steady flow conditions. So to see how a full-scale turbine will perform under surge motions, you don't have to calibrate the model with an actual moving turbine. You can just take measurements from a fixed turbine and plug that information into the model. So I mentioned that this model can predict amplitude and phase by accounting for additional dynamics. But that comes at the cost of ignoring nonlinear effects. Notably, the linear model does not predict any change in mean torque or power with increasing surge velocity. And then also the model is not accounting for any sort of unsteady aerodynamics. So if we find cases where the model doesn't match the data, then we can point to these as potential causes for the discrepancy. Now, with that said, let's see how the model does. And for our example case, it looks like the model is doing a pretty good job of capturing the turbine dynamics. And so now from there, let's expand our scope to the full range of surge frequencies and amplitudes that we tested. So here is the amplitude of the generator torque on the left, and the amplitude of the aerodynamic torque on the right. Each has been divided by the corresponding surge velocity to represent a transfer function gain, which is then non-dimensionalized. And we plot these values against surge frequency, which is normalized by a characteristic frequency that we pull from our model. Colors from light to dark represent increasing tip speed ratios, and the lines are model predictions. And I'm also not showing the data from the trapezoidal cases, but you can trust me that they follow similar trends. So as you can see, the model does a good job in capturing the trends in the data over the range of surge kinematics tested, and as per our ansatz, the measured torque looks something like a low-pass filter on the left here. Now there are some exceptions at low tip speed ratios, and then at high tip speed ratios and high frequencies, which may suggest additional dynamics at work, but we'll come back to these later. Now, if we look at the phase of the torque waveform with respect to the surge velocity waveform, we see that the model also captures trends in the measurements here quite well. And again, we note that there are exceptions at low tip speed ratios. Now, these results suggest that we are able to predict trends in the torque amplitude and the phase using only data from steady measurements to inform our model. So that covers the time-resolved dynamics. Now, what about the average power? So here we plot the period averaged power, normalized by the steady reference case for all tested waveforms against the non-dimensional surge velocity. And since the linear model is simply a line at unity, we see that the model becomes less insightful at high surge velocities. And we note that these deviations from the linear model are actually correlated with tip speed ratio. At low tip speed ratios, the mean power falls off as the surge velocity increases. And then at high tip speed ratios, the mean power increases up to 6% above the steady reference case. And recall that we saw similar tip speed ratio effects in the amplitude and the phase data as well, so there must be some additional dynamics at play here that are not captured by the first order linear model. So we'll start by looking at the low tip speed ratio cases, and we think these can be explained by the onset of stall or flow separation on the turbine blades. As shown schematically in this vector diagram, a low tip speed ratio corresponds to a high angle of attack on the turbine blade. With the addition of high surge velocities, the local angle of attack on the turbine blades may then exceed the static stall angle, which would lead to an increase in drag and eventually full turbine stall. And we've shown in our experiments that at low tip speed ratios, if we add too much surge, we can effectively kill the turbine. However, at high tip speed ratios, the local angle of attack is lower, and so stall is a less likely explanation. One hypothesis that we can make is that the deviations in this regime could be due to unsteady aerodynamics, such as some dependence on surge acceleration. Another hypothesis is that our linear analysis ignored some sort of crucial nonlinear effects. The quasi-steady model that I mentioned earlier, for example, retains a cubic dependence on wind speed, and here we can see it seems to do a better job in capturing the upward trend in the averaged data. Now, it's hard to say much more than that with our current data, so we are planning a series of flow measurements to probe at these potential unsteady and nonlinear contributions. But for now, I will conclude with our main findings. Our experiments showed that the first-order linear model that we derived can capture the time-resolved dynamics of the turbine in terms of amplitude and phase, and it does this, again, without any foreknowledge of those unsteady dynamics. Additionally, our experiments showed increases in the time-averaged power by up to 6% above the steady reference case. And this further motivates studies of the dynamics that are not captured by the first-order linear model, which might allow us to find new ways to increase the efficiency of wind energy systems by leveraging streamwise motion and unsteady fluid mechanics. So with that, I will conclude my presentation and acknowledge the many people who have helped make this work possible. So I want to thank you for listening, and if you have any questions, please feel free to contact me. Thank you.